Hello guys, welcome back to my channel. This is Saman Usmani, pursuing BTech in Computer Science Engineering, specialization in AI and data engineering at Lovely Professional University. Today in this video, we are going to talk about tree data structure. So, tree data structure are fundamental data structure in computer science that organize information in a hierarchical manner. They consist of nodes that store data and are connected by edges, forming a tree-like structure. Unlike linear data structure like arrows or linked list, trees provide a more efficient and intuitive way to manage and navigate complex information. This information will explore the key characteristics of tree data structure, their advantages, and the essential operations that can be performed on them. So let's talk about advantages of tree data structure. So advantages of tree data structure are first advantages is efficient data retrieval. Trees allows for fast data lookup and retrieval, particularly in scenarios where data is organized in a hierarchical manner. The branching structure of trees enables efficient searching and navigation, making it easier to find specific information. And the second advantage is flexible organization. Trees can accommodate data that has a natural hierarchical structure such as file system. Like in file system, there are root folders. Then uh, in root folder there are subfolders. Then in subfolder there are many folders. So this is the hierarchical manner. Organizational charts. Another example is organizational charts. Like in a company, first comes CEO, then COC, then CEO, like this. And the decision-making process. This flexibility allows for better organization and representation of complex relationship between data elements. Dynamic resizing. Trees can be easily expanded or contracted by adding or removing nodes making them adaptable to changing data requirements. This dynamic nature is particularly useful in application where the data size of structure may evolve over time. So I'll tell you the tree data structure on whiteboard. This is the tree data structure, and these are the component of tree data structure. First component is node. Node is node is the structure in which some value is uh, given. Like these all the circle in which the value is given. These are the nodes like 10, 25, 40. These all are the nodes and root. And the in the tree, the first node of a tree is root. So the what is the first node of this tree? 10 is the first node of this tree. So this is the root of the tree. Then leaf. The last nodes of tree are called leaf. Like 40, 50. These are all leaves of the tree. Then child. The nodes between root and the leaves are called childs, like 20, 80, 30, 80. These are all the childs. And the nodes, the node uh, from which this child is connected, it is those nodes are called parents, like 8, 30, and 80. These nodes are connected to 30. So the parent node of these child nodes is 30. And subtree are the trees uh, in in a big tree. The the like this is a subtree. In this tree, this is the subtree, and in this is also a subtree. So these are the subtree in a tree. So now I will tell you the traversal in a tree data structure. We can consider tree traversal problem as a printing every key of the tree exactly once. Tree traversals are of two types. First is breadth, breadth first, and the second is depth first. In this video, we will talk about depth first. So depth first are three types: in order traversal, pre-order traversal, post-order traversal. In order traversal, we will traverse the tree. First, we will traverse left subtree, like we will traverse first left tree, then root, then right subtree. And in pre-order, we will traverse first root, then left, then right. And in pre-order, we will traverse first left subtree, then right, then root. So try this example. Uh, First, we will traverse this tree in order. So uh, like this, first in order, first we will first traverse left subtree. So the left subtree of this tree is 20. So 20 will come first, then we'll go to root. And the root of this tree is 10. Then we'll go to right, and the right is 30. And in pre-order traversal, first we'll go to root. Then the root of this tree is 10. Then we'll go to left. And the left of this tree is 20. Then right. Right is 30. Then post-order traversal. In post-order traversal, we first go to left subtree, left, sorry, left of this tree is 20. Then right. Right is 30. Then 10. Root. Root is 10. So this is the three order traversal of this tree. In uh, in order, we will first go to left subtree, then root, then right subtree. In pre-order, we will first go to root, then left subtree, then right subtree. In post-order, we will go to first left subtree, then right subtree, then root. So uh, example of these are the explanation. This is the explanation of tree traversal in order, pre-order, and post-order. Now let's do some more example. First, make a tree. 10, 30, 20, 40, 50, 70, 80, and last is 60. So this is the tree. So let's find the in-order traversal of this tree. In order. So in in-order traversal, we will first go to left subtree, and the left subtree of this tree is 20, and the 20 is another root of a subtree. Then the left subtree, the left node of uh, left node of this tree is 40. Then 40 comes first. Sorry, oops, 40. After that, 40. Then root is 20. Then 20 comes. Then right is in the right there is a subtree, and there is a root of a subtree. Then it will not count here. Then the left node of this root is 70. Then the 70 will come, 70. Then root 50, 50 will come. Then right 80, then 80 will come. Now the root of this tree will come, and 10. Then left is none. Then right is 30, and it will not have left. And so 60 will come, 60. So this is the in order traversal of this tree. Now come to pre-order traversal. In pre-order traversal, we'll first go to root. The root of the tree is 10. Then we'll go to left. The left of this tree is 20. Then 40 will come, because the mm, left of this tree is the sub tree is 40. Then right will come, right is 50. Then 50, after 50, 70, then 80, then 30, then 60. This is the pre-order traversal of this tree. Then post order post order traversal is in post order traversal, first left is come, left is 40. Then right of this is right of this subtree is, this is the root. Then this is uh, another root. Then right of this tree is 70, 70. Then uh, the oh, sorry, left. Then Right will come, right is 80, 80 after 80, 50 will come, then 20, 60, 30, 10. This is the post-order traversal of this tree. Like after that, now, so now let's write the Python codes on traversal. Just go to Visual Code Studio and first create a class called node. Class node. Then create a constructor def and give it to value key. Then self dot key is equals to key. Self dot write. We are initiating the value of right. Sorry, first initiate the value of left because in order traversal, first we have to come from root, then left, then right. So first we have to initiate the value right as null. Then slash dot right equals to right is equals to sorry null. So this is the constructor for making the tree. Now make a function of in order traversal in order initiate it as a root. Then if root is not equal to none, then in order root dot left. When root is not equal to none, then call the function and give it to value root dot left. After that, print root dot key uh, here is first come left because in order traversal first we have a count from left subtree to then root then right subtree. So in this function we first call the left subtree then root. After that we call in order root dot right. This is the function for in order traversal. Then write driver code, make the tree root is equals to first node of the root tree is 10, then root dot left is equals to 20, then root dot right is equals to 30, then root dot right dot left is equals to node 40, then root dot right equals to node 50. Sorry, 50. Then call the function uh, in order. Then call the in order function in order root. So what will be the output of this function? Let's run it. The output of this function is 20, first come 20, 10, 40, 30, 50. This is the in order traversal. So now let's make the function of pre-order traversal. Def pre-order, give it the initial value is root, then if root is not equal to none. So in pre-order traversal, what will we do? We'll do first traverse the root of the tree, then go to left subtree, then go to right subtree. So in this code, we'll first print the root of the tree. Print root dot key. Then we'll go to left subtree. So call left subtree order root dot left, then call right subtree root dot right. So let's comment out this function. Then call this is the call for pre-order traversal. Okay, 1 second. This is the call for pre-order traversal. Then run this code, and you can see the output. The first uh, we print the root of the tree. The root of the tree is 10. You can see here root is equals to 10. Then we'll go to left subtree, then traverse on this tree, then this go to right subtree. This is the pre-order traversal of a tree. Now let's make another function on post-order traversal. Post order. This is also initial value of this function is root. Then if root is not equals to null, both the all the traversal are the code of all the traversal are same. You can see here, but only one difference. It will be the order of calling function is different in all the traversal. So in post-order traversal, we'll first traverse all left subtree. So post order equal to left dot root. Then we'll go on right. So call right function, right subtree. Then print the root of the tree. So let's comment out this. Then call post order, and let's see the output this code. Sorry, this is root dot left and root dot right. It's not correct. So the output of this function, first we'll go for left subtree, then right, and then root of the tree. So these are all three traversal we have studied, and after that, let's come to binary search tree. So what is binary search tree? A binary search tree is a hierarchical data structure that organizes data in a sorted order, allowing for efficient searching, insertion, and deletion operation. In a BST, each node has at most two children. Like in the BST, at most two children is present in the VST, a left child and a right child. The key property of a VST is that for any given node, all node in its left subtree have keys less than its own key, and all nodes in right subtree have keys greater than its own key. Like uh, um the left node of binary search tree is always smaller than the root node of the binary search tree, and the right node of binary search tree is always greater than the root node of binary search tree. So I'll show you the binary search tree. Let's This is 2020. So the this is the left node of binary search tree. So what is the property of BST? The left node of the BST is always smaller than the root node. This is the root node of this tree. Then the left node of uh, this tree is always smaller than this node. So 10 is coming here, and the right node of binary search tree is always greater than the root node. 30. This is the binary search tree. Now let's talk about insertion in the BST. So insertion in a BST involves finding the appropriate position for the new node based on its key and then adding it as a leaf node. Starting from the root node, compare the key of new node with the key of current node. First compare the new node with the key of current node. Then if the new node's key is less than the current node, move to the left child. So the new node, the node which we want to insert is less than the current node, then move to left subtree. If it's greater, move to right subtree. And the node which we want to insert in the binary search tree, if it is greater than the root node, then go to right subtree. Repeat this process until you reach the null child pointer, then insert the new node. Repeat this process until you find the null child pointer and insert this value on there. Then coming to deletion. Deletion in VST can be a bit more complex. There are three cases to consider. First case is deleting a leaf node. The first case is the deleting the leaf node. Like leaf node of this tree is 10 and 30. Simply remove the node from the tree. Then second case is deleting a node with one child. Replace the node with its child. Then if child is there, if the node which you want to delete is between one child, then remove the child and replace it with the child. Then third case is deleting a node with two children. In this case, find the nodes in order successor, which is smallest node in its right subtree. Replace the node's key with the successor key, then recursively delete the successor from its subtree. After deletion, ensure that BST property are maintained by appropriately adjusting the tree structure is necessary. So now let's coming to the code of insertion of binary search tree. Now let's come to coding part of the insertion in binary search tree. So first we make the tree, then we make function called insert, then root key is the value initially in this function. If root is equal to none, then re return node key. So this is the first case of insertion. Like if root is equals to, if the tree is none, then insert the key which we want to, then return the key which we want to insert. Now elif root dot key is equal to key, then return root. So this is the second case uh, in which the key which you want to insert and the root of the key both are same, then return root of the key. Let's make another case. Alif root dot key is greater than key is greater than key. So root dot left is equal to insert root dot root dot left key. This is the third case. If both above two cases is not considered, then going to this case, if root dot key the is greater than key, the key which we want to insert, it is greater than uh, it is smaller than the root node, then go to left subtree and insert the value in it, on which place it will be. Then last case is else root dot right is equals to insert root dot right key. This is the last case in which the value, the key which you wants to insert is greater than the root, then go to left subtree and insert it in their reliable position. So
So this is the code for insertion. Now we have to write the any traversal in order, pre-order, any of those traversal, because we have to reach the node where we want to insert the value. So we have to write the in order traversal code. So def in order root if root is not equal to none, left sorry in order is equals to root dot left. Now print the root dot key in order root dot right. This is the Inorder traversal function. Now we are calling the insert function. Result is equals to insert root comma. Now we have to give the value which we want to insert in the tree. 15. We want to insert 15 in the tree. Then we have to print result print in order result. Now let's check the output. So this is the output for the insertion. 20, 10, then 15 is added here, then 40. These are the output of insertion.
Now come to the code of deletion. So I have written the code here. First uh, we have to write a function called del node. In this function uh, we have to retain all the three case which I have told you in the previous. So this is the root dot write is equals to del node. This is the code for the root is equal to the node which we want to delete. Else if root dot left is equals to none, then return root dot right. If root dot next left is equals to none, then return root dot right. If root dot right is equals to none, return root dot left. And else sucks is equal to get successor root dot right comma key. So this is the function for deleting the node. And in this code we have also written a traversal, because when we delete a node from the tree, we have to traverse the whole tree. So that's why we have to written the function here for Inorder traversal. Then Inorder traversal is this. Then uh, see the output of this code. So this is the output for this code. This is the code for deletion the node from the tree. So let's finish this video. Uh, this, uh, this is uh, this is all about the tree data structure and deletion insertion of tree data structure. Thank you and have a nice day.